by just agreeing that points in the plane were represented by vectors and that linear transformations are the appropriate functions to look at from the plane to itself, and by using the definition of a linear transformation and examining basis vectors, we very quickly arrived at the matrix representation of linear transformations. So a linear transformation F applied to a vector V, well, a V is a column vector X with components X, Y, then F can be carried out, F applied to any vector. Really, all you need to pin down F to characterize F is these four constants A, C, B, and D, and they produce the matrix for F. And what A, C, and B, and D are, or even say A, B, C, D, in normal order, is they are the components of F applied to the two basis vectors I and J. In general, how a matrix representing a linear transformation is constructed. The columns of the matrix representing the linear transformation are the results of applying the linear transformation to each of the basis vectors of the domain in turn. Okay. So we discussed that. Then we examined the whole issue of what, how this matrix representation worked, other aspects of it. And two of the important things are really the main one important thing is that when you compose different linear transformations, that is equivalent to multiplying their matrices together. So the matrix that represents the composition of two transformations is exactly multiplying together the individual matrices that represent F and G. So if A represents F and B represents G, then the matrix that represents F after G is A multiplied by B. Okay? And order is important here. The matrix B multiplied by A would represent the transformation G after F, which in general is going to be different because it makes a difference the order in which you do things. True. Okay, we then looked at, I won't rehash the whole lecture, but we then looked at affine transformations and isometry. So isometries, this was the main class of function between vector spaces that we were interested in. Functions that didn't change the distances or angles. Sometimes they're called kind of like rigid transformations. They don't bend stuff around or rescale stuff. They just kind of pick stuff up, maybe rotate it, translate it, reflect it. And we arrived at a classification into 6 different types. So we had, well, some trivial types, the identity. We had translations, rotations, reflections, and so-called glide reflections. Glide reflections are a composition of a reflection and a translation, where you reflect first in some axis, reflect in some line, and then you follow it by a translation parallel to the line that you're reflecting. And going along with that, we have this notation. So RC, the notation RC theta refers to rotating the plane about the point C by an angle theta anticlockwise. The notation QC theta refers to reflecting the plane in the line that goes through the point C and that makes an angle of theta with the x-axis. And QCG theta was a glide reflection, where the reflection is QC theta, as I just explained, and G is the glide vector. And then to work with those in calculations, we need a bunch of properties about how to compose and how to express the transformations in certain ways. So there's a bunch of equations here. In general, remember that the standard form for an isometry is going to be this kind of form. So you represent it as a linear part. So lambda A is a linear transformation represented by the matrix A. You do that operation first, and then afterwards you apply a certain translation. That's kind of the standard form, translation after linear operation. And there are equations here in these pages towards the end that take the 3 general types, rotation, reflection, and glide reflection, and show you how to get them into standard form of translation after linear operation. Rotation in the case of rotations and reflection in the case of the reflection and glide reflection. And then we started doing some exercises. We also I'll revise homogeneous coordinates when we get to the MATLAB part. Okay, so let's jump across to the overhead. Or first of all, I'll take any questions. Any questions or queries that you'd like to ask at this point? Okay, so let's get going with it again. We'll jump into an example and work with some of these things in detail. So, we'll consider the standard form transformation F. So this is in standard form, so we're translating by the vector 1, 1. And we're doing this after, so composed with the reflection Q pi over 2. So we're going to consider this, and we're going to classify this as a reflection or glide reflection. So this transformation, which is a reflection, then Q the angle theta, well, when we leave out the vector, by convention, we mean reflection in a line through the origin. So this is a reflection in a line through the origin, which makes an angle of pi over 2 at the x-axis. So that's better known as the y-axis, reflection in the y-axis. That's that reflection. And then we're following that by a translation t by the vector 1, 1. So it's a translation kind of 45 degrees up in that direction. It's of length root 2. But, so this is a reflection in a line through the axis followed by a translation. But according to the classification scheme, this itself must be equal to maybe a rotation about some point, or maybe a reflection in some axis away from the origin, or maybe a glide reflection. So we'd like to arrive, so what this question is asking us is, of all the types of isometry listed on page 26, well, of all those 6 types, which type is this? Okay. Well, as with all these things, it's a good idea to draw a little sketch just to help you see what's going on. So we'll draw our XY axes. And, well, the Q operation is reflection in the y-axis. Just do a little squiggly line and 2 arrows to indicate that that's not standard notation in these, just my own notation to indicate that we're reflecting the plane in the y-axis, okay, because that's the line that goes to the origin and makes an angle of pi over 2, the x-axis. So this is Q, if you like. And the translation part, well, I want to think of this vector 1, 1. So this is the translation part. This is Q, pi over 2. Translation by vector 1, 1. Now, what we want to do is we want to examine the translation part. This is just a general translation vector at the moment. However, the translation follows the reflection. And associated to a reflection, there are 2 important directions that you can associate to any reflection. See, this translation vector is just some kind of a translation. The translation vector could be pointing in any direction. But what's the operation that's done first, so in this composition, the operation that's done first is the reflection. Now, if you reflect in any line, there are two kind of special directions associated to that reflection. And they are, one is the direction parallel to the reflection axis, and the other one is the direction perpendicular to it. Okay. Because those are the two directions that, under reflection in this axis, they kind of remain the same. I mean, if you're in a line which is going in the direction parallel to the reflection axis, after you reflect it, it's still going in the direction parallel. If you're a line, or if you're a vector going in a direction perpendicular to the reflection axis, and you reflect in the y-axis, you're still going perpendicular to it. So those are kind of special directions. They have nice behavior with regard to the reflection. And they also form a basis of the plane, parallel and a direction perpendicular to that. So what we'd like to do is take this, take the reflection, the translation vector. So we want to express the translation vector. This is the translation vector 1, 1, in terms of the basis. And so in general, the basis formed by the directions, so parallel to and perpendicular to the reflection axis. Oh my God, how do you spell parallel? Is that how you spell it? 2 L's in the middle? 1 R, 1 L, yeah. By direction parallel and perpendicular. That's another one. Perpendicular. 60% certain that's me. Not sure. Parallel and perpendicular to the reflection axis. So how does 1, 1 decompose with regard to that? Decomposes in a fairly straightforward way. So we want to express it in terms of the basis formed by directions parallel and perpendicular to the reflection axis. So the direction parallel to the reflection axis is the direction of the unit vector j, and perpendicular is the unit vector I. So we just have to express it in that kind of standard form. So this is 0, 1 plus 1, 0. But I mean, if you were to tackle some other similar type problem, if the reflection axis was not just the y-axis, was at some general kind of direction, the decomposition of the translation vector that you'd use here would be into these two components, parallel to and perpendicular to the reflection axis. So now we have another look at f. Now f appears as, let's write our f like this. So it's q pi over 2. But now the translation, I've expressed the translation vector as the sum of these two. So translating by a sum of two vectors is just the same as translating through one of them and then translating through the other one. So I can split apart this original single translation into a composition of two translations. So I'm going to do translation by vector 1, 0 there. And then lastly, finally, we'll translate it through 0, 1. Yeah. I'm re-expressing f like this. You see this pair now at the front, this translation in by the vector 1, 0 after reflection in the y-axis. We just examine what happens. We can tell which reflection that's going to be. Because if you look, see, performing these two, you take a general point over here, it reflects over to the other side, and then you translate it by 1 unit this way. So that means if you look at the collection of points which are on this line, and that's the value 1/2. If you look at all the points on the line parallel to the y-axis, located at x equals 2, x equals 1/2, when you apply these two parts of f to it, you reflect in the y-axis and then translate by the vector 1, 0, you see that all these points remain in the same place, yeah? Because the reflection hops them over to the other side, but then the translation moves them straight back to where they were. So this line here, the line through the point to 1/2, 0, which is parallel to the x-axis, that line is unchanged by this reflection followed by this translation. We'll call this line L. So note that the line L is fixed by T10 after Q pi over 2. So that means the composition of these two must be reflection in the line. So this composition must be reflection in the line L. Because it's a reflection and the line L is preserved by the reflection. So it must be L is the reflection axis for T10 after Q pi over 2. So F now, I can write it as, I've still got the T01, but now I've got Q, so now it's in the form Q C theta. It's reflection, and I'll choose as the reference point to 1/2, 0, and the angle is pi over 2. You could choose any point along L, but I choose the one that's on the x-axis just as a kind of standard one. But now when we're looking at it, now it's looking like a glide reflection, okay? Because now F is of the form, we'll do this reflection. So this reflection is reflection in the axis that runs through the point 1/2, 0 and is parallel to the y-axis. So reflect in that line and then translate by the vector 0, 1. But this translation is in a direction parallel to the reflection axis. So matching the two together, this reflection followed by a translation in a direction parallel to the axis, overall then that's a glide reflection. So F is in fact a glide reflection, QCG theta, a glide reflection, where the vector C, the reference point on the line, we can take as a 1/2, 0. G, the glide vector, well, that's unique, the vector G0, 1, and the angle theta was pi over 2. And this is the general situation. In general, this is the general behavior. I.e., if T is any translation, and if T is any translation, then T after Q theta, so translation after a reflection in a line through the origin, making an angle theta with the x-axis, this is probably a glide reflection. Well, let's say is always a glide reflection unless, so there's one special case, unless t is perpendicular to the reflection axis of q theta. See, if t is just purely perpendicular to the reflection axis of the reflection q theta, then the effect of the translation after the reflection is simply to change it to a reflection through another line. There's no glide component. But that's special, you know, it's a special occurrence when the translation is exactly perpendicular to the reflection axis. In a general composition, some reflection followed by some translation, generally it won't be so aligned like that. Generally, the translation vector will decompose like we decompose this one. It will decompose into a certain amount in the direction parallel to the axis of reflection and a certain amount in the direction perpendicular to the axis of reflection. So the effect of the one that goes perpendicular to the axis of reflection is to shift the reflection axis, and the effect of the one parallel to the reflection axis is that's the glide component of the overall glide reflection. Yes, question. Why half? So it's a half because the length of this translation, which went perpendicular to the original reflection, so the original reflection axis is the y-axis. It's then followed, when I wrote it like this, that reflection is followed by a translation of distance 1 perpendicular to it. So what I was looking for the points that under this composition, the composition of these two here, remain unchanged. So fixed, so you have to be a half, you hop over a half the other way and then you get sent back. Yeah. So if this length here was changed, that would just have the effect of moving this a little bit. Yeah. Okay. And the choice of the point half zero as opposed to any other point on that line is just purely my own choice. Just because a half zero is, say, the simplest point. Equally well, you could choose any other reference points along that. Any other queries or? Okay, then I've got an extra problem sheet here to hand out, which has a bunch of extra problems. And if you've got the assignment sheets on you, you'll notice that the pen and paper problems are kind of on this type. So the first few pen and paper problems on the assignment. All right. So let's look at some of these questions. So the first one. Right. This first question is a similar type of one to the one we just looked at. Different, but similar. So the question we just looked at was a composition of a reflection and a translation. And the question was, well, figure out exactly what type of reflection or glide reflection it is. Give a precise geometric description of the overall effect. Here we're dealing with the rotation. So we're rotating by some angle. So when it's just r an angle, when it's just the angle specified, this means rotation about the origin. So the center of rotation is the origin. If the vector is included in the r notation, then that's the center of rotation. So we're rotating about the origin by pi over 3, 1/6 of a full turn. And then we're translating in this translation vector 2, 1. And the question is, as it says there, determine the representation for f as a single rotation. So what single rotation is this? Now, if you think about it a little bit, it kind of has to be a rotation. I mean, if you could imagine yourself looking at the plane, but if you zoomed out miles away from the plane, to carry out f, okay, you rotate things around the center. So you'll see, if you could see loads of stuff in the plane and you were far away from the plane, you'd see the stuff rotate. And then you'd see the translate by 2, 1. Now, if you're really far away from the plane, you wouldn't notice the translation. It'd just shift things a tiny bit from your perspective being far away from the plane. So really, the major component there is just the rotation. Okay. So really, the overall effect should really be the same kind of rotation. It should still be a rotation by the same angle, pi over 3. But maybe the center of rotation is not located at the origin, but located somewhere slightly different. So we just want to analyze this now and see if we can figure out where the center. So really, we're just looking for the center. We're looking for the center of rotation of this composition. So this is the further problems number 1. Really, we're looking for the center of rotation. Oops. Really, we're looking for the center of rotation of translation by 2(1) after rotation by y/3. Now, where is it going to be? Good question. Where's it going to be? Well, let's draw a sketch of the plane. Let's draw in the translation vector. That's kind of easy to draw in. So the 2 translation vectors, maybe something like that. So let's call this D. So I'll call this translation vector D. So D is 2(1). The vector 2(1). That's the translation vector. But before doing that, you rotate by π/3. Now, so we're suggesting that overall this is, okay, it's called F in the question. So F overall is going to be rotation through some center to an angle of, well, some angle. It'll turn out the angle is π/3. But the unique thing about the center of rotation is the center of rotation doesn't move. When you rotate the plane around a center of rotation, the point about it is every point moves except for the point that you're rotating around. That stays, you fix the plane on that point and you just rotate the plane. So every point moves except the center of rotation. So what we're searching for here is in some ways you can think of it as searching for the solution of f of x equals x. So f is this composition, and we're searching for the vector, and there's one unique solution of it, such that f of x is equal to x. Well, here's a sketch of what the point x looks like. See, the first rotation is around the origin. So here's the origin somewhere. So I'm drawing a slightly separate diagram. Okay, I've already messed it. It's already not very accurate, but there's the translation vector D. And we'll make this big angle. I'll just draw the angle symbol out here. The big angle is theta. So the way we think about this is we're rotating about theta. So we imagine a cone, if you like, or two lines at angle theta. And we've got our translation vector. So we pick up the vector and we just fit it into this cone with angle theta, which is coming out of the origin. And it'll fit nicely in. Remember, D is a vector, so it has a particular direction. So we can move D around the plane, but it's always in this fixed direction. It has a fixed length. So we just find the cone coming out of the origin into which this vector D fits perfectly like that. Okay, it just touches one edge of the cone here. Cone isn't the right word. It's like a fan. We call that fan at angle theta. Thinking about the fan where the vector D fits neatly into there. And then you can, then we can see the fixed point here. Where's x in this picture? X is in this picture. The solution to that equation is here. Where in the picture is it? Center? No. Huh? Yeah, X is not moving. So whereabouts in this diagram is X? Sorry? The tip of the arrow. Yeah. Because remember, we do the rotation first and then the translation. So like, let's look at a general point. General point out here, it rotates by theta and then it translates. Well, that kind of looks like it is back there. If you think about a point here, when it translates by theta, it'll move across to here, or just the origin, and then you translate and move away here. But of all the points in this diagram, the one at the tip of the arrow is the unique one. Because the rotation sends it out to here, and then the translation moves it back. So X is here. Actually, sorry, the picture is a little bit unspecified. I mean, which particular fan are we talking about? Because this fan could be positioned anywhere. I could have two lines coming out here in a direction theta, but it's the one into which D fits neatly. And it's the fan which has this unique property that when you bisect the angle, so when you look at theta over 2, when you bisect the angle, we're looking at a perpendicular to D. This should be bisecting D as well, and it's slightly off there. So the bisector of the fan at angle theta over 2 is perpendicular to the translation vector. So we have a fan of angle theta, two lines separated by angle theta, whose bisector, the bisector is just the line in the middle of the fan, whose bisector is perpendicular to D. Perpendicular to D. Then, well, let's stop calling it C, let's call it C. C, the center of rotation of F, the overall composition, C is at the head of D. So the tip of the arrow is the head of D. Vectors have heads and tails. The head is where the vector ends up, and the tail is where it starts. So what is C? So what we want now, okay, we kind of geometrically located C by argument in terms of the angle and the translation vector. Now let's pin it down. Exactly how do you express C in terms of the angle theta and D? So let's say that so E, let E hat be a unit vector in the direction of the bisector. I.e. perpendicular to D. Well, D I know is 2, 1, so I could say E, the vector E would be, well, what's the direction that's perpendicular to that? It's going to be -1, 2. You flip the coordinates and change the sign. If you had 1 minus 2, that'd be coming out exactly, I mean, it's still perpendicular to D, but it'd be coming out the other side. So E is that vector, this is perpendicular to D, and we can change it into a unit vector by dividing it by its magnitude, and its magnitude is root 5. So we can 1 over root 5 by minus 1, 2. So that's a unit vector in this direction, e hat. Now we can say that C is equal to a certain amount times E hat plus 1/2 of D. Where does that come from? That comes from looking at that picture and thinking, well, how do I get from the origin to C or X? I've written it as X in the diagram, but that's the point. C. How do you get from the origin out to C? Well, you go a certain amount along out the bisector of the fan, which is the direction E hat, the direction of the vector E, the perpendicular direction to D. We go a certain amount along that until we hit this point here, along D, and then we go along half of D. And that will bring us to the center point there. Now, lambda is you can determine, lambda comes from the length of a triangle. So you've got a right angle triangle there. So lambda is the length there. We know this is magnitude D over 2, that base, and we know the angle is theta over 2. So for us, that's pi over 6. So we can determine lambda from that information. We don't have the hypotenuse, so we're looking at the adjacent and opposite sides, so we should talk about tan of the angle. So we see tan of pi over 6 is whatever it is, opposite over adjacent. So magnitude of D over 2 lambda. Yeah. So magnitude of D, well, D is magnitude root 5 as well. So that implies lambda is root 5 over 2 times the tangent of pi over 6. So from the angle theta, so the pi over 6 comes from a half of theta. So it comes from the original setup of the equation. So we know what D is, so we know what a half D is, and this formula gives us lambda. Is pi over 6 a special angle? Is that a nice? Pi over 6. Does your calculator tell you if pi over 6 is a nice angle? Should know that off the top of my head. Everybody know that stuff there? Tangent of pi over 6. I suspect it's nice, but I'm not quite sure. Yeah, I worked it out before, just for that one. So tangent of pi over 6 is 1/3 of square root of 3. Tangent of pi over 6 is 1/3 of the square root of 3. So this is 3 root 5. Sorry, what did it say? 1/3 of the square root of, that's different. 1/3 of the square root of 3. So that's 1 over the square root of 3. So 1 over the square root, so we can put root 3 up there, 2. So root 15 over 2. So we'd finally get C being this lambda value, root 3 root 5 over 2 times vector minus 1, 2 plus 1/2 of D. 1/2 of D is 1/2. So there's your C for you. And the angle is still a third of pi. Okay, the angle is 35. So F is equal to the rotation around the center C for an angle pi over 3. 3 like this. Okay. And that is the typical behavior, where any old rotation followed by any old translation, that composition will be the same rotation by the same angle, but around some other center point. Okay. So this is the general behavior. That translation after rotation by theta will be rotation through some other center point by the angle theta. Square brackets. So translation after rotation around the origin by angle theta will in general be a rotation around some other center point by the angle theta. Where the center point C comes from, what did it came from? It came from theta and the translation, as in this example. Okay, yeah. Any questions on this? And the reason we're doing these is, well, we'd like to be able to have this nice description of 2D transformations. We're going to do some 2D animations shortly using them. But we're building towards the kind of the real application we want to be able to handle is to be able to handle transformations of three-dimensional space. Okay. We want to be able to talk, really we want to be able to talk about rotations in three-dimensional space. Now, there's a lot more room in 3 dimensions, so rotations, the structure of rotations is a lot richer in 3 dimensions. There's more things you can rotate around. And rotations are the key operation in taking our virtual environment, which is just modeled abstractly in the computer memory, or in the vector model that the computer is holding, and getting from that abstract vector model to an image on the 2-dimensional screen. And that is done, remember, we talked about there's a virtual camera within the virtual environment. The camera is pointing in a certain direction, and then you want to do some kind of projection onto the camera screen or onto the camera sensor, and that becomes your 2-dimensional image. Now, those operations are handled using 3-dimensional transformations of various kinds, chiefly rotations and translations. So that's what we're building towards. We're building towards having a thorough description of rotations in 3 dimensions. Okay. I did show you a picture last time of the wallpaper thing you need for assignment 3. So I've got a little video demonstration of that here. I think what we'll do at this point is, I'll show you that now. And so this is just a little bit before the break. I'll show you that now and just set up that assignment for you. And then after the break, we'll do something different. I'll show you a MATLAB example. So it's some example MATLAB programming to produce a kind of a similar type of 2-dimensional animation. Okay. So we'll hop back to, oh yeah, this is just, so yeah, I stuck the video in here. So this is just like a 2-minute video or something. So I'll just play this. Here you can see my wallpaper example. This is the kind of thing you're producing for assignment 3. Okay. And you can see here
here that the motif has been repeated on 6 by 6 grid. When I move my code, you can see that the motifs are rotating in place and rotating in place, growing and shrinking. And we're doing this in adjacent motifs are rotating in opposite directions, and also growing and shrinking in opposition, so that motifs that are beside each other, one is at its largest, its neighbors the smallest. So for your assignment, you will need to choose a basic motif that is required in the assignment, and then work towards producing this kind of
Right. If my evil plan has worked, I've hypnotized you all. You'll all be dreaming tonight. Kill you, kill you, kill you. Okay. We'll wait and see tomorrow if it's worked. Okay, now, what was going on there? So I referred to the motif. So the motif was the big letter K. And it was doing various things. It was rotating and it was scaling and so on. Now there's some skeleton code. Well, let's just look at when we look at the assignment guide, I mean, it spells out, it gives a verbal description of that. What you want. So you want a wallpaper pattern which repeats on a 6 by 6 grid some basic motif. And use something interesting. Don't just maybe use the letter of your name, or use some interesting shape. Don't just use a square. Use something a bit kind of interesting. And the requirements here specify what it should be doing, that rotating and pulsating stuff. When you look on Moodle as well, okay, so you're not expected to do this from scratch. So there is some skeleton code that we've set up for you. And God, I want to be able to tell. Okay, now I won't spend ages because it's not syntax highlighted either. But well, actually, okay. So just there's a skeleton outline of a MATLAB M file. It's got a main script in it and some helper functions, and there's plenty of instructions there in the comments. So that's the thing you're going to start working with to produce the video. Now, after our break, we'll take our break now. And in the break, I'm going to do, not that wallpaper example, but I'm going to do a similar kind of exercise with a basic motif and transforming it around the plane. So I'll talk you through that one, and the starting off code file I'm using for that one is quite similar to this. Okay, so we'll do that as the exercise in the second half, and if we have time remaining, then we can maybe look at the assignment questions itself, or I'll answer any queries you have, or look at some more of these example problems. So shall we give ourselves 20 minutes from now? 25 minutes, 20 minutes? 25? Okay, so, well, split the difference, 23. So we'll be back here at 25 minutes past 3. So we'll start again at 25 past. Past 3. That clock, they haven't moved it back yet. But still on.